In today's artificial intelligence class, we will see the robotic perception from 5th unit. Under this class, we will see the different robotic perception methodologies like localization mapping. Under this, we will see one example, that is simplified kinematic model for mobile robot. After that, the sensor model. So this is somewhat difficult and this is somewhat easier one. After that, we will see other types of perceptions like temperature, audio and video perception, and then the machine learning robotic perception. Under this we will see one example, that is autonomous driving domain and self-supervised learning. So these are the things we will see in today's class. Robotic perception. Here perception means this is robot. The robot will perceive the environment by using sensors. Right? When come to robotic perception, the robot map the sensor measurement into the internal representation of the environment. Right? And this process is somewhat difficult because the sensors may produce some noisy data and the environment may also be a partially observable, unpredictable and sometimes dynamic environment. So with this type of environment, the perception is somewhat difficult and also the sensor also produce some noisy data, isn't it? So this is called as the problem of state estimation. Estimating the state is difficult here. The good internal representation for the robot have three properties. The first one is they contain enough information for the robot to make good decisions. Right? So to take good decision, enough information required. And second one, they are structured, that is robotic perception are structured so that they can updated efficiently. Okay, if they are structured, then updation will be very efficient, otherwise it will be difficult. And they are natural, that is perception is natural because the robot will perceive the real time environment, right, in the sense that the internal variables correspond to natural state variables. This is important in the physical world. Okay, so the internal variables correspond to natural state variable in the physical world. So these are the properties for good internal representation of robotic perception. The robotic perception can be viewed as temporal inferences. So the temporal inferences from the sequence of actions and measurements. Okay, so the sequence of based on the sequence of actions and measurements, we can infer the data, which is illustrated by the dynamic Bayes network. So this is dynamic Bayes network. Example, dynamic Bayes network. Here three variables are there. The first one is xt. So this is state. Xt is nothing but the state of environment at time t, right? At the time t, how the state will be. So this is represented by xt. And next one is zt. Zt is observation received at time t. So zt is nothing but observation received by sensors at time t, right? And at is nothing but action taken after the observation received. Okay, see, after the observation received by using sensors, then decision will be taken place. Based on the decision, the corresponding action will be performed on the current state, right? So these three variables are important here. Now we need to compute the new belief state. So from here we need to compute new belief state, the probability of xt plus 1, the probability of xt plus 1 such that z12 t plus 1 comma a12 t plus 1 a12 t. Okay, right. From the current belief state, the probability of xt such that z12 t a12 t minus 1. Okay, see, from this state we need to compute this particular state. Okay, so the new observation is zd plus 1, this one zd plus 1. Okay, here the probability of x t plus 1 such that z12 t plus 1 comma a12 t, which is equal to alpha into probability of z t plus 1 such that x t plus 1 integration of, here we introduce a new the integration here in this equation. So probability of x t plus 1 such that x t comma a t multiplied by probability of x t such that z12 t comma a12 t minus 1 into dxt. This particular equation states that the posterior probability over state variable x at time t plus 1, this particular probability, variable's probability is calculated recursively from corresponding estimate one time step earlier itself. Okay, that is t plus 1, one time step earlier itself. This calculation involves the previous action, this is the previous action at, and the current measurement zt plus 1, that is zt plus 1. Okay. The posterior probability, this particular probability is a probability distribution overall state that captures from past sensor measurement and controls. Okay. So based on the previous sensor measurement and the previous action, based on that only the posterior probability will be computed, right. The equation recursively estimate its location by incrementally folding in sensor measurement, that is the camera images and robot motion commands. Okay. The equation recursively estimate the location of robot, that is incrementally folding the sensor measurement, that is by using the camera images and the motion command of the robot. So based on this the location will be identified. The probability, that is this particular posterior probability, is called as transition model or otherwise motion model, and the probability for this zt plus 1, which is called as observation model, which is otherwise called as sensor model. Okay. The first perception model is localization and mapping. Here localization is a problem of finding out where the things are, including the location of robot in the environment. So which is called as localization. That means inside the environment where the things are placed and where the location of the robot. So this is called as localization. For example, the robot manipulator must know the location of objects they seeks to manipulate. Okay. Or otherwise the manipulator should know the path of robot as well as the current location of robot. Now let us consider a mobile robot which will be moved slowly on flat 2D world. Okay. So in the flat 2D world, one mobile robot is moving, and assume the robot is given an exact map of the environment. That is, the robot know very well about the source location and the destination. Okay. So this know very well about the path also, and the robot is defined by two Cartesian coordinate x and y. Okay. In which particular place in the environment, x comma y, as well as the angle degree theta. Okay. And if we arrange those three values in a vector, then any particular state is given by xt. Xt means the current state at time t, which is equal to the coordinate x coordinate at time t, y coordinate at time t, and theta at time t. Okay. So this is the current location of the robot. And now let us see the simplified kinematic model for the mobile robot under localization and mapping method. So the robot is shown in circle with an interior line. So this is robot. This circle is nothing but robot with interior line, that is directed line, right. So this makes the forward direction of this particular mode. That means the robot is moving in this direction. Here the state, current state capital XT, which consists of xt comma yt, that is x comma y, position of the robot, and orientation is theta. So from this x, this will move in this angle, particular angle, so theta t. Okay, now the new state xt plus 1, okay, from this x place it will move to xt plus 1. Okay, in this state is obtained by update the position and orientation of this robot, that is omega t delta t. So this particular place, right, and also shown the landmark at xi yi observed at time t. Okay, after time t the robot will move here, okay, which is called as xi comma yi. So the ith time the place of robot. And this is the range scan sensor model, which explains the pose of particular robot. Okay, so two possible robot poses are shown in this diagram. Okay, here the given range scan is Z1, Z2, Z3 and Z4. See, this is the range scan of this particular robot, and this is the range scan of this particular robot, right? And this much more likely that the pose on first the left generated, and second the range scan, and third one the pose on the right. Okay, first it should be generated, then range will be scanned, and the right side movement will be taken place. The next one is sensor model. The sensors in the robot detects the stable and recognizable features of environment, which is also called as landmarks. So inside the environment there are more number of landmarks that should be identified by the sensor model, and each landmark the range and bearings are reported. Bearings is nothing but the behavior, isn't it? So those should be reported, and the sensor model is used for an array of range sensors. That is, so many sensors are there, each of which has fixed bearing relative to the robot. So inside the robot many number of sensors are there to identify the landmark, right, and such sensors produce the vector of range values. So each sensor will produce a vector value. Sometimes noise will also be included in the sensors, okay, and this noise will be corrupted by Gaussian noise. When comparing the range scan model and landmark model, range scan model means in the environment a particular range will be scanned by the robot sensors. Landmark model means the landmarks are fixed and identified in the environment, right. So the range scan model has somewhat advantage when compared to landmark model, because there is no need to identify the landmark, okay, until it required. So until otherwise it is required, no need to identify the landmarks in the environment in the range scan model. So this is advantage. Other type of perceptions. Other type of perception means the perception model other than localization or mapping model. Okay, here the robots also perceive temperature, smells, audio signals and so on. So these are also sensed by the sensors. Okay, so many of these quantities can be estimated using variants of dynamic Bayes networks. Okay, by using Bayes networks we can estimate all those signals, right, and all that is required for such estimators are conditional probability distributions. And the perception model characterized into the first one, evaluation of state variables over time. That is, in the environment what are the state variables are there that should be evaluated by the perception model. That is the first characteristics. And second one is the sensor models that describes the relation of measurements to state variables. Okay. So what are the relationship between the state variables, that should be referred by the sensor model, right. The robot is a reactive agent and which is represented with well defined semantics, right. And there are two techniques in perception model. First one is probabilistic technique and second one is statistical technique. When come to probabilistic technique, this is good for hard perceval problems like the localization and mapping problem. Those are somewhat very heavy. In such problems we can use this probabilistic technique. But when come to statistical technique, the problem is, that is, the program is very heavy but it will give very simpler solutions, and these are also best for effectives in practice, right. So there are two types of techniques which are used in perception model. One is probabilistic technique and second one is statistical technique. The machine learning in robot perception. The machine learning is very important when the best internal representation is not known. So in this situation immediately we can go for machine learning methodologies. One common approach is the machine learning methodology is helpful to map high dimensional sensor streams into low dimensional space, right. So this type of machine learning is called as unsupervised machine learning method, and this is also called as low dimensional embedding. Low dimensional embedding, that means the sensor, for example video camera, from the video camera the input will be coming continuously, that is the stream of input that should be mapped with low dimensional space. Okay, this called as low dimensional embedding, and the machine learning makes it possible to learn sensor and motion models from data. Sensor and motion models from data while simultaneously discovering the suitable internal representation. Okay, all these things possible only because of machine learning. The machine learning technique enables a robot to continuously adapt the huge changes in the sensor measurement. If there is changes in sensor measurement, immediately the robot should adapt for that. Okay, for that changes. For example, suppose we walk from sunlight space into dark neon light room. Okay, we are coming into the neon light room from outside sunlight. Okay, inside the neon light room the things are very much darker, okay, when compared to sunlight. Okay, and the changes of light source also affect all the colors. Okay, because the neon light dominates the green color. Okay, and somehow we not to notice the changes. Okay, that means we adopted this particular neon light color. Okay, if we walk together with the people to the neon lit room, see in this room, we don't think suddenly their faces turned green. Okay, because of this neon light the faces color will get changed and our perception quickly adapts. Our perception quickly adopts the new lighting condition. Okay, and our brains ignores the differences. Which difference? Sunlight to the neon light. Okay, because our brain immediately adopts the changes and it ignores the differences and it keep on doing work continuously. Autonomous driving domain. This adaptive perception technique enables robot to adjust such changes in the perception. Right? For example, let us see this autonomous driving domain. Here the sequence of drivable surface classifier results using adaptive vision. So here we are having three different images. This is A, B and C. In A, only the road is classified as drivable. Okay, so the stripped lines are the road surface. See, this is road, right. So on the road the vehicle can move on. Okay, but the V-shaped dark line shows where the vehicle is heading. So but see, this particular way the robot have to move. Okay, this is the path of robot. Okay, but up to this only road is present, after that there is no road. But when come to second diagram, see here the vehicle is commanded to drive off the road. Okay, the vehicle have to move offside the road also into the grassy surface. So these are grassy surface, that is the dark surface. Okay, now the classifier begins to classify some of the grasses are drivable. So the immediately machine learns that some of the grasses also drivable, and when come to see, the vehicle has updated. So immediately the machine learning technique inside the vehicle updates its model of drivable surface to correspond to grass as well as road. Okay, so these are grassy surface. On the grassy surface also the vehicle can move, hence it immediately update the road as well as grassy field which the vehicle can move on, right. This is how an unmanned ground vehicle, which is nothing but the automatic car, isn't it, adopts its classifier of the concept of drivable surface. Okay, how it identifies the drivable surface otherwise. See, after that a mixture of Gaussian technique, which is similar to EM algorithm. EM algorithm means expectation and maximization algorithm, isn't it? So is then trained to recognize the specific color and texture coefficient of small sample patch. Okay, so the small sample patch of road as well as the grass field, okay, which are suitable for driving on site, and the images are results of applying this classifier into full image. Self-supervised learning. The method that make robots collects their own training data is called as self-supervised learning. So the robot collect their own training data. Okay. In this instance, the robot uses machine learning to control short range sensors. That works well for land classification into sensor that sees much further. That means the sensor have to identify the whether the path is road or grass. Okay, so this is called as short range. So within this short range it will sense the road. It allows robot to drive faster, showing down only when the sensor model says there is a change in the road. Okay, the sensor immediately identifies the changes and that will inform to the robot. Okay, this needs to examine more carefully by the short range sensors. So far we have seen the robotic perception from 5th unit in artificial intelligence, and we have seen what is robotic perception, and then the localization and mapping methodology with an example called the simplified kinematic model for mobile robot and sensor model, and then we have seen the other types of perception and machine learning in robotic perception. So here one example, that is autonomous driving domain and self-supervised learning. All these things we have learned in today's class. The next class we will see another important topic from 5th unit. For more information, please go through your textbook. Thank you.